Hey everyone, we're going through the 2.4 worksheet. And so for a warm up, we have Amy, Ben, Jared, and Maya are four friends. If they compete in a race, how many possible results are there for their rankings? First, second, third, or fourth place. So because order does matter on this one, we're going to use permutations because there's like rankings involved, so the place does matter. So the formula, we're going to pick, we've got four friends. A permutation, we're going to pick four places. So this would be, I'll write the general formula over here so you guys can see what I'm plugging into. This I'm just taking right from your slides. Okay, so we're going to have 4 factorial over 4 minus 4 factorial. Whoops. So that's equal to 4 factorial over 0 factorial, and 0 factorial is just 1. It's a special case. So then up top we got 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24, times 1 is just 1, so we have 24 possible results. Next, their biology teacher plans to put them in the same group. No other students, just these four, for a lab activity. How many ways could the teacher group them together? So now this order does not matter. We're gonna, this is kind of ridiculous. This is just like a warm-up. I guess this is kind of, I'll show you how to do it with the formula, but this is a combination because the order does not matter, but we're picking 4. It's 4 choose 4, so it's a little like how many ways can we pick 4 groups of students if you only have 4 options, right? There's only one way to group them. Okay, but that is the same thing as 4 choose 4, the combination, okay? Which our formula for a combination, hold on, is 4 factorial over, 4 minus 4 factorial times 4 factorial. Okay, so this would be 4 factorial over 0 factorial times 4 factorial. This is just 1, so I'm going to eliminate that. And we still get 4 factorial over 4 factorial, which is 1 way, which makes sense because like if we had 4 students and we could only put 4 in a group, like that's the group, right? And it doesn't matter if we switch up the order of like Amy, Ben, Jared, Maya, or Maya, Jared, Ben, Amy, it's the same group, 1 way. All right, so that's your warm up. Next, the county fair planners are trying to decide a schedule of performers for the main stage on Saturday afternoon. They have 24 entries, but only 5 of them will get a spot. There's some concern over the order in which the bands will play, so they must consider more than one order when they select their group of 5. How many possible schedules do they choose from? So we got to ask ourselves, does the order matter on this? And apparently it does. There's some concern over the order, so that is an important, it's important in this case. Maybe the main stage, like the last performer, is going to have more people in the crowd, so they need to, consider who's closing this fair or whatever we're doing. So the order matters, so we're going to use a permutation. We've got 24 possibilities, choose 5. So this is 24 factorial, all divided by 24 minus 5 factorial. Whoops, I have to see here, this is on the outside. Okay, so we've got 24 factorial, all divided by 19 factorial, for 24 minus 5. So if I were to write this out, we've got 24 times 23 times 22 times 21 times 20 times 19 times 18, forever and ever. Well, until we get to 1. And then down here we've got 19 times 18 times 17, until we get to 1. So then this part repeats. 19 divided by 19 is just 1. 18 divided by 18 is 1. 17 divided by 17. 16 divided by 16. On and on. So we can simplify those two. That's just 1. So our total possibilities are 24 times 23 times 22 times 21 times 20, which I will do in my calculator. And we have, let's see, 33, 5,100,480 possibilities, possible lineups. Performers, I guess. Okay, lineups. There we go. Okay, next one. There are 12 high school bands competing, or what am I saying, bands? I don't know where I read that, but that's okay. 12 high schools competing in a basketball tournament. How many ways can they be placed? First, second, third, all the way to 12 at the end of the basketball tournament. So this is kind of like our warm-up. The ranking does matter, so this is a permutation. So we've got 12 teams, and we're going to put them into 12 spots. 12, choose 12. So we're going to write in here, this is going to be 12 factorial, all divided by 12 minus 12 factorial. Dang it, I keep doing this in the wrong order, you guys. This does not go on the inside. That's the confusing thing that I'm doing to confuse you. Shouldn't be confusing, I'm just doing that. Okay, so 12 minus 12 is 0. So we're 0 factorial is just 1. All right, so we've got 12 factorial. This is in your calculator somewhere if you've got one at home. I don't know. Let's see where it is. I have to find it again. I'll work on that. But you can also use a website, a permutation calculator. But what's happening is we're just doing 12 times 11 times 10 times 9, on and on. So I'll do that in my calculator. All right. Whew. We have 479,001,600. All right, I gotta go backwards. So 679,001,600 possibilities for our tournament. So possible rankings or tournament outcomes or something. Okay. Next. 2 volunteers are needed to manage a water station at the local 10K race. Jordan, Dave, Karen, Louis, Maria, and Lily have all signed up to be race volunteers. How many pairs are there to choose from? So this one, the combinations, or is a combination because the pair doesn't matter, right? The order doesn't matter. Jordan and Dave is the same pair as Dave and Jordan. So we've got 1, 2, 3, 4, 5, 6, and we're going to choose 2 for pairs. So this is a combination. So we've got 6 factorial all over 6 minus 2 factorial times 2 factorial. All right, so we've got 6 times 5 times 4 times 3 times 2 times 1 up top. This is 4 factorial, so 4 times 3 times 2 times 1, and then we got another 2 times 1 in there. So here, those simplify. So we have 30 over 2. When we multiply 6 times 5 is 30, 2 times 1 is 2. So we have 15 possible pairs, 15 pairs available. All right. Permutations. Order matters. These are good notes here. Combinations. Order does not matter. Okay. Second page. A group of 10 seniors, 8 juniors, 6 sophomores, and 5 freshmen must select a committee of 4. How many committees are possible if the committee must contain the following? So 1, there must be 1 person from each class, or B, sorry, 1 and B. Part B, there can be a mixture of any classes. All right, so we need to use that little flow chart on your notes for this. So first thing we need to ask ourselves are, can the items be repeated? And the answer is no. Like if we pick one of the seniors, that same senior can't be picked again. Like, I don't know, Bob is a senior. We can only pick Bob once. He can't be on the committee twice because there's only one Bob, right? So the items cannot be repeated. Is there more than one category? For this one, yes, there is. There are seniors, juniors, sophomores, and freshmen. Those are our 4 classes, and we are going to multiply our possibilities here. All right, so for each category, we need to ask, am I only selecting one item per category? And the answer is yes. So I'm only picking one senior because I'm selecting a group of 4, so I can only pick one. And so you would just enter the number of choices. So I've got 10 seniors, so I'm going to choose 10. Well, it's really 10 choose 1, which is just 10. Okay, so just entering the item. Then how many juniors do I have? Well, I have 8. And then I have 6 sophomores and 5 freshmen. Okay, so this will give us our possibility for having one of each on each or on the committee. So we have 10 times 8 times 6 times 5. So we have 2,400 possible committees. All right, next we're going to continue. Now there can be a mixture of any classes. So it does not matter if we have 4 seniors or 4 juniors or whatever, like 2 sophomores and a senior and a junior, it does not matter. So we are going to take our total, and order does not matter. So this is going to be a combination. So we've got 10 plus 8 plus 6 plus 5. This is our total. What would this be? 18 plus 11 is 29. So we have 29 total students. 18 plus 11. Sorry, my brain feels slow. Okay. So we've got 29, and we're going to choose 4. And the order does not matter. So this is just 29, choose 4. So this would be 29 factorial all over 29 minus 4 factorial times 4 factorial. So we've got, this would be 29 factorial over 25 factorial times 4 factorial. So when we simplify this, we'd have 29 times 28 times 27 times 26, but then the 25s would cancel out for there. All divided by 4 times 3 times 2 times 1. All right, so I'm going to do this in my calculator. 29 times 28 times 27 times 26. And then I'm going to divide by 4 times 3 times 2, and times 1 is the same thing. So we get 23,751 possibilities. Possibilities. All right, and that makes sense. Like we're going to have way more possible outcomes if we're not limiting to like each grade. Okay. Then we're going to evaluate 5, choose R. I guess oh man, I'm like learning this. I could do this in our other worksheets. That's good to know. So this is this one, you guys. 5, choose R. And we're going to plug in 0, 2, 3, and 5. I would just use your permutation calculator if you would like. Those answers then would be 5, choose 0. I'm going to do it right in my computer. And I can drag this over so you guys can see it. So this is that website. I've got 5, choose 0, and I'm going to be looking at the combination section here, not permutation. The answer is 1. And then I've got 5, choose 2. So just change that. We have 10. 5, choose 3. is also 10. And then 5 choose 5. It's going to be 1, I believe, but let's see. 1. Hooray. So you can use those. Answers are here. All right, last problem. Actually, just kidding. There's 3 more. A standard deck of playing cards contains 52 divided into 4 suits and 13 cards in each, where each suit has 3 face cards, king, queen, jack, and 10 non-face cards. That's talking about our regular standard deck of cards. So how many different 5-card hands containing exactly 3 aces are possible? So we need to basically figure out how many combinations are there for a 5-card hand that have 3 of a kind. So we need to go through our flow chart again. So I'm just going to read through it. Can these items be repeated? No, they can't. There's only one type of each card in the deck. Is there more than one category? Yes. We've got, for our categories, we've got our aces. And then we've got the non-aces in our cards. Okay, and so then it says, does the order of the selection matter? No, it does not. Right? We can pick, any variety of aces or any other card. The order doesn't matter. We're just picking cards. So we are going to use combinations. So for our aces, we've got 4 possible aces, and we're going to choose 3. All right, so then that's our first box times. Okay, now we cannot pick the 4th ace because that'd be 4 of a kind. Okay, so we have 48 other cards that are possible, right? We have 52 in a deck. We can't take any of the 4 aces. So we've got 48 possibilities, and we're going to choose 2 of them. So 48, choose 2. All right, so I'm going to just use my calculator. So 4, choose 3. These are my aces. And I want the combination, so I just have 4 times. I've got 48 cards, and I'm going to choose the other 2 for my 5-card hand. So 1,128. Well, 4 times 1,128, I'll do in my regular calculator. That is 4,512. 5-card hands with three aces. That's amazing, isn't it? It's so many. 3 of a kind is a lot more possible than our 4 of a kind that we looked at in the notes. Okay, so how many different 5-card hands are containing 3 of a kind are possible? Well, this is really how many possible 3 of a kinds there are, whatever suit. We found aces, but this could be for 2s, 3s, 4s, 5s, 6s, whatever, on and on. So we're going to multiply this times the 13 possible cards, right? 13 cards each. So we have 58,656 possible 3 of a kinds. Okay. 3 of a kind, 5-card hands. Okay. There we go. And last little bit. We're using distinguishable permutations of identical items. So this is where we take n, these are our total number of items, and we divide by the number of repeats. Okay, so how many unique ways can we arrange the word peer? So we've got 4 letters, and we've got e's that repeat, so divided by 2 factorial because it repeats 2 times. So we've got 4 times 3 times 2 times 1, all divided by 2 times 1, bam, bam. We have 12 possible arrangements. Okay. And last one, how many unique ways can we arrange the letters in Mississippi? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters total, 11 factorial on top. Now, we have 1, 2, 3, 4 I's. So we've got 4 factorial underneath. So we got 4 I's. Okay, we've got 1, 2, 3, 4 S's. And we've got 1, 2 P's. All right, do I have any other repeats? No, good. So this would be, let's see, we take out 4 factorial, so this is 11 times 10 times 9 times 8 times 7 times 6 times 5. No more 4s because we eliminated 4 times 3 times 2 times 1. But then I got another 4 times 3 times 2 times 1 from this guy. Another 2 times 1 from that. So let's do this. 11 times 10 times 9 times 8 times 7 times 6 times 5 divided by 4 times 3 times 2 times 2, right? Times 1, those are in there too, but it's just the same thing. So we get 34,650 possible ways to arrange the letters in Mississippi uniquely. And that is the end of your 2.4 homework.